Right now, on a mountaintop in Chile, a camera the size of a small car is taking a picture of the sky every 20 seconds. And within roughly 60 seconds of each exposure, an alert is already landing on astronomers' computers around the planet. No camera ever built has photographed the universe at this resolution. No survey has ever mapped the changing sky this fast, this completely, this relentlessly. It is not a telescope anymore. It is a real-time alarm system for the entire visible universe. Stay with me, because 8 months ago, this exact system caught something spinning so fast it should not exist. If you're new here, this channel breaks down real astronomical discoveries the moment the data confirms them. No filler, no fiction, just what the papers actually say. So, if that sounds like your thing, the subscribe button is right there. Let us go back to the beginning. The machine responsible for all of this is called the Vera C. Rubin Observatory, sitting at 8,800 feet on the summit of Cerro Pachon in northern Chile, jointly funded by the U.S. National Science Foundation and the Department of Energy at a cost of roughly $800 million. It is named after Vera Rubin, the astronomer who, working with colleague Kent Ford in the 1970s, produced the first hard observational evidence for dark matter by noticing that stars on the outer edges of spiral galaxies were orbiting just as fast as stars near the core, a result the standard physics of the time had no way to explain. That naming is not sentimental. Decoration. It is a statement of purpose, because the observatory built in her name exists specifically to hunt for the things the current models cannot yet account for. To understand why this facility is different from every telescope that came before it, you need to understand what most observatories actually do, and why they were built that way for good reason. Traditional telescopes are specialists. They point at one target, gather light for hours, sometimes nights, and produce a single, deep, static image of a small patch of sky. That approach makes sense if you already know exactly what you're looking for: a specific galaxy, a specific star, a specific patch of the cosmos worth the investment of time. It is not designed to catch something happening right now, somewhere unexpected, that nobody thought to point a telescope at in the first place. For most of the history of astronomy, that trade-off was simply the cost of doing business, because no single instrument could realistically watch the entire sky at once. Rubin was built to break that trade-off completely. Its telescope has an 8.4-meter primary mirror paired with the largest digital camera ever constructed for astronomy, 3,200 megapixels, roughly the resolution equivalent of about 1,570 modern smartphone cameras stitched into one. Every image it takes covers a patch of Sky 40, times the size of the full moon, and the observatory's 10-year survey, called the Legacy Survey of Space and Time, is designed to photograph the entire visible southern sky roughly once every 3 or 4 nights, over and over for a full decade. First light, the observatory's first engineering images through the complete telescope and camera system, came in 2025. Full survey operations formally began in the summer of 2026. Over that decade, Rubin is projected to catalog roughly 20 billion galaxies, 17 billion stars in our own Milky Way, and more than 6 million objects in our own solar system. Read that again: 6 million solar system objects, most of which nobody on Earth has ever seen before, because nothing has ever looked in the right place at the right time often enough to notice them moving. Each pair of 15-second exposures captures a swath of sky roughly 40 full moons wide, and the entire observing schedule is automated, cycling through the visible southern sky night after night, with almost no human intervention required to decide where to point next. Compare that to how astronomy worked for most of the 20th century, where a researcher had to write a proposal months in advance, justify exactly why a specific patch of sky deserved a specific number of hours on a specific night, and then hope the weather cooperated when that single allotted window finally arrived. Rubin removes that bottleneck almost entirely. It doesn't wait for a hypothesis. It just watches, everywhere, on a fixed and repeating schedule, and lets researchers sort out afterward what mattered. That combination, massive field of view, extreme resolution, and constant repetition, is what makes Rubin, in effect, the first true motion picture camera ever pointed at the universe, rather than a still photograph camera. And it is precisely that capability that, within its very first months of real operation, turned up an object that shouldn't, by the standard rules of asteroid physics, be able to exist. Here is the number that matters: 1.88 minutes. That is how long it takes an asteroid called 2025 MN45 to complete one full rotation on its axis. Now translate that to something you can actually feel. Earth takes 24 hours to spin once. The International Space Station, moving fast enough to circle the entire planet in about 90 minutes, is still nearly 50 times slower than this asteroid's spin. 2025 MN45 completes a full day-night cycle in less time than it takes to watch 2 commercial breaks. And this is not some tiny pebble tumbling chaotically through space, the kind of small fast spinning fragment astronomers have caught before without much surprise. This object is 710 meters across, nearly 7 football fields laid end to end, roughly the length of Manhattan's Central Park Reservoir. Here's where it gets worse. Astronomers have understood for decades that most asteroids larger than about 150 meters across are not solid rock at all. They are what planetary scientists call rubble piles, loose collections of boulders, gravel, and dust, held together by nothing stronger than their own weak mutual gravity. The same way a pile of sand holds its shape only because gravity keeps pulling every grain downward and inward. That model is not a guess. It comes from decades of spacecraft visits, radar measurements, and direct sample return missions that found exactly this kind of loosely bound structure again and again. And that model comes with a hard physical limit. If you spin a rubble pile fast enough, centrifugal force at its surface eventually exceeds the weak gravitational glue holding it together, and the object simply flies apart. The same way a spinning top made of dry sand collapses into scattered grains once it spins past a certain speed. For a main belt asteroid, that fragmentation limit sits at roughly 1 rotation every 2.2 hours. Spin faster than that as a rubble pile, and you cannot stay in one piece. That's not a theory under debate. That's basic, well-established physics. 2025 MN45 spins 70 times faster than that limit. Sit with that for a second. 70 times past the point where a loosely bound rubble pile should have shredded itself into a spreading cloud of gravel and dust, and yet it hasn't. It's still there in one coherent piece, 710 meters wide, spinning once every 1.88 minutes, as if the rulebook simply didn't apply to it. The discovery, published January 7th, 2026, in the Astrophysical Journal Letters by a team led by Dr. Sarah Greenstreet of the University of Washington's Dirac Institute, emerged from exactly the kind of data Rubin was built to catch. Repeated brightness measurements taken during the observatory's earliest test observations in April and May of 2025, before the full 10-year survey had even officially begun. Out of 76 asteroids where the team could reliably measure a rotation rate, 19 turned out to be unusually fast spinners. But 2025 MN45 stood alone. It is, according to the observatory's own announcement, the fastest rotating asteroid larger than half a kilometer that anyone has ever measured, and by a comfortable margin. Clearly, this asteroid must be made of material that has very high strength in order to keep it in one piece as it spins so rapidly, Greenstreet said when the discovery was announced. Her team's calculations put the required cohesive strength at something close to solid rock, not the loosely bound gravel and dust structure researchers expect from an object this size, but something closer to a single, coherent chunk of stone strong enough to resist being torn apart by its own spin. What most people are not seeing when this story gets summarized as fast asteroid found is the actual weight of that conclusion. It means at least some large asteroids are built completely differently than the standard model assumes, and there was no reliable way to know that until an instrument existed that could watch enough of them, closely enough for long enough to catch the outliers. Here is where this stops being an abstract physics curiosity. Every space agency on Earth that has ever discussed planetary defense, the practical, funded effort to prevent a dangerous asteroid from hitting our planet, has built its deflection strategies around the rubble pile assumption, because that's what most surveyed asteroids of this size actually turn out to be. NASA's 2022 DART mission deliberately slammed a spacecraft into the asteroid moonlet Dimorphos, specifically to test how a loosely bound rubble pile absorbs and redirects a kinetic impact. And the mission succeeded in nudging its orbit in exactly the way rubble pile models predicted. But a solid, monolithic asteroid does not respond to an impact the same way a rubble pile does. It transfers momentum differently, fractures differently, and in a worst-case defense scenario, needs a completely different kind of nudge, delivered years or decades in advance to shift its path away from Earth. Knowing which type of object you're actually dealing with before you need to deflect it is not a footnote. It's the entire difference between a mission that works and one that doesn't. And this is precisely the kind of information planetary defense researchers have historically had almost no way to gather in advance. Determining whether a given asteroid is a rubble pile or a solid body used to require sending a dedicated spacecraft to visit it directly. An expensive, years-long undertaking that has only ever been done for a small handful of objects in the entire solar system. Rubin changes that math substantially because a rotation period alone, measured from Earth through nothing more than repeated brightness readings, can now flag which asteroids are structurally unusual before any mission ever needs to be planned. That is the quiet, unglamorous value underneath a story like this one. Not just a strange fact for a headline, but a genuinely useful early warning tool for figuring out which of the millions of rocks now being cataloged actually deserve a closer look. Getting an instrument capable of catching an anomaly like this into working order was never guaranteed, and the road to Rubin's first light was, at more than one point, genuinely uncertain. The observatory's camera, the 3,200 megapixel heart of the entire project, spent over a decade in design and construction at the SLAC National Accelerator Laboratory in California before it was ready to travel anywhere near Chile. In May 2024, the finished camera, roughly the size of a small car, was loaded onto a chartered Boeing 747 freighter for the flight from San Francisco to Santiago. That got it into the country. It did not get it up the mountain. From Santiago, the camera still faced a 12-hour truck journey along winding Andean roads to reach the observatory's remote site. And partway through the logistics planning, a national trucking strike in Chile threatened to blockade the exact route the convoy needed to take. For the team responsible for the most expensive single instrument the observatory would ever build, watching a labor dispute threaten to strand a one-of-a-kind camera on a highway shoulder was not a minor inconvenience. It was the kind of moment that turns a carefully planned decade-long project into a waiting game, decided by events completely outside anyone's control. The convoy made it through before the strike closed the road, and the camera reached the summit intact. That was only the first crisis. Once installed, the camera had to be positioned with almost impossible precision relative to the telescope's mirrors. Engineers placed it by careful calculation to within about 3 millimeters of its ideal position, an extraordinary tolerance for a piece of hardware that size. It wasn't quite good enough. Because Rubin's field of view is so extraordinarily wide, even that tiny 3 millimeter offset showed up in the earliest test images as glowing donut-shaped blobs of light where individual stars should have been sharp points smeared into rings by the slight misalignment. Engineers used those very donut images as a diagnostic tool, adjusting the camera's position in small increments, image after image, night after night, until the light finally snapped back into focused points. Then came a second, more dangerous problem, discovered during the camera's commissioning phase. The cooling system meant to keep its light-sensitive detectors near absolute zero began allowing internal temperatures and pressures to creep upward. If left unresolved, the warming risked releasing trapped gases inside the sealed camera housing, gases that could then condense directly onto the delicate sensor surfaces. A contamination event that engineers on the commissioning team described as potentially catastrophic for the long-term health of the entire instrument. The probability of it happening was considered low. The consequences, if it did, were not. Engineers spent weeks diagnosing and correcting the cooling system before the camera was cleared to keep running at full capacity. Every one of these crises happened. In the shadow of the same basic reality, there was no factory-fresh replacement camera sitting in a warehouse somewhere. There was exactly one. As one of the commissioning scientists put it plainly at the time, you can test every system exhaustively in a lab, and reality on the mountain is still always slightly different than what the lab predicted. That is not a complaint. It is simply the nature of putting a completely unprecedented instrument through its paces for the first time, 20 years after the project was first proposed, with an entire decade of planned science hanging on getting it right before the shutter ever opened for real. The stakes of that commissioning period were not abstract either. A single serious failure during those final testing months, a contaminated sensor, a permanently misaligned mirror, a damaged focal plane, would not simply have delayed the survey. It could have meant re-engineering hardware that took over a decade to design and build in the first place on a mountaintop thousands of miles from the labs capable of doing that work at a cost measured in years, not weeks. Every adjustment engineers made during commissioning was, in effect, a bet placed against that outcome, made one careful command and one diagnostic image at a time. Here is what is happening right now in 2026. Full survey operations for the Legacy Survey of Space and Time officially began on June 30th, 2026, after checkouts and commissioning work pushed the original early 2026 target back by several months. In its very first night of real-time alerts on February 24th, 2026, the observatory issued roughly 800,000 individual notifications to astronomers worldwide. New asteroids, exploding stars, flaring black holes, anything that changed in the sky compared to the previous image of that same patch. Each one distributed globally within about 2 minutes of being detected. That number is expected to climb, night by night, toward a target of roughly 7 million alerts every single night once the survey reaches full operational tempo. In its first month and a half of early test observations alone, before the official survey had even started, Rubin had already logged more than 11,000 previously unseen asteroids, including 33 near-Earth objects and 380 objects out in the distant, icy Kuiper Belt region beyond Neptune. Data scientists are currently working through the observatory's second major data preview, released in stages through the first half of 2026, containing an order of magnitude jump in data volume over everything gathered before it. And even now, researchers studying that flood of images are still refining how to correct for subtle optical distortions in the camera's field of view. a technical challenge that directly affects the observatory's ability to measure the faint gravitational lensing. Signal, it needs to probe the nature of dark energy itself. None of that is a sign the mission is behind schedule or in trouble. This is simply what the first year of operating an unprecedented instrument actually looks like up close. Refinement layered on refinement, long after the public announcements have already moved on to the next headline. And there's a specific, already locked-in date on the calendar that tells you exactly how fast this machine is about to start proving itself. Under Rubin's official operations schedule, the observatory's first full public data release, called DR1, the moment its complete first year of science-grade data becomes available to researchers everywhere, not just a preview, is scheduled for 12 to 14 months after the Legacy Survey's official start date. The survey began on June 30th, 2026. Count forward, because this isn't speculation. It's the observatory's own published construction and operations timeline. That puts DR1 landing somewhere between the end of June and the end of August 2027. That is the point at which the full weight of Rubin's first uninterrupted year of nightly sky scanning, every asteroid, every supernova, every flare, every anomaly it caught while nobody was looking, becomes available for the entire global scientific community to comb through at once. Every fast-spinning outlier like 2025 MN45, currently sitting unnoticed somewhere in that data set, is, as of this moment, still waiting to be found. Now, the honest part, because this discovery does not fully resolve itself, and pretending otherwise would be dishonest. Scientists know 2025 MN45 must have unusually high internal cohesive strength to survive spinning this fast. That conclusion comes directly from basic centrifugal physics and is not seriously disputed. What remains genuinely open is how it got that way, and there are two competing explanations currently on the table. One possibility is that 2025 MN45 formed as a coherent, solid body from the very beginning, born directly from a large parent asteroid that shattered in a way that left this particular fragment as a single dense, monolithic chunk rather than a loosely reassembled pile of rubble. The other possibility is that it started life as a more typical rubble pile, but a relatively recent high-speed collision transferred enough angular momentum to spin it up dramatically, and over time, that same spin caused looser surface material to be shed away, leaving behind a denser, more tightly bound remnant core. Both explanations fit the available data. Neither has been confirmed, and researchers studying the object have been clear that distinguishing between them will likely require additional observations. More precise, measurements of the asteroid's shape, its surface composition, and ideally a direct look at how its brightness changes across multiple full orbits. Data Rubin itself is positioned to keep collecting as the 10-year survey continues. Zoom out from this one asteroid, though, and the deeper story here isn't really about rock strength or spin rates at all. It's about what happens when a civilization finally builds an instrument capable of watching rather than just looking. For nearly all of the history of astronomy, discovery meant pointing a telescope at something you already suspected was interesting and hoping you were right. Rubin inverts that entirely. He watches everything indiscriminately on a fixed and relentless schedule and lets the anomalies announce themselves. 2025. MN45 wasn't found because someone theorized it should exist and went looking. It was found because a machine happened to be watching that patch of sky on that night, logging brightness the way it logs brightness for literally everything else, and a graduate researcher's software noticed the numbers didn't fit the model. That is a fundamentally different way of doing science than humanity has practiced for most of its history, and it means the next genuinely strange discovery, the next object that breaks a rule nobody thought was breakable, is not a question of if. It is sitting right now in a dataset nobody has fully looked at yet, waiting for the right comparison to reveal that it doesn't belong. Think about what that shift actually represents. For most of human history, the limiting factor in astronomy was access. Who could get time on a telescope? Who could afford the equipment? Who happened to be looking in the right direction on the right night? Rubin doesn't eliminate human judgment from the process, but it does something almost as significant. It removes luck as the primary bottleneck for catching something rare. Every patch of sky gets watched on the same repeating schedule, whether or not anyone believes there's something interesting there. The asteroid didn't have to be discovered by someone brilliant enough to guess it existed. It only had to exist and be caught by a system patient enough to look at everything equally, without prejudice about where the next anomaly might be hiding. There's a particular image from Rubin's earliest test observations that keeps circulating among astronomers, informally, almost like a keepsake. A single wide-field frame nicknamed the Swarm of Asteroids, showing thousands of faint-colored streaks cutting across a field otherwise dominated by a distant spiral galaxy. More than 4,000 solar system objects captured in one exposure, over 2,000 of them never recorded before that single photograph. Somewhere among those anonymous colored lines, unlabeled and unremarked upon at the time, is 2025 MN45 itself, a 700-meter world spinning nearly 70 times faster than physics says it should be able to survive, photographed by accident, alongside thousands of others just like it that nobody has bothered to look at closely yet. It sat there, undiscovered, indistinguishable from any other faint streak of light, until the E software finally asked the right question of the right pixels. It is still out there tonight in the dark between Mars and Jupiter, spinning once every 1.88 minutes, holding itself together by a strength nobody can yet fully explain, utterly indifferent to the fact that it briefly became the most talked about rock in the solar system. So here's everything in one breath. The Vera C. Rubin Observatory, an 8.4-meter telescope carrying the largest camera ever built for astronomy, began real-time sky alerts in February 2026 and full 10-year survey operations that June, designed to photograph the entire visible sky every few nights for a decade. Within its earliest test observations, before the survey had even formally begun, it caught an asteroid called 2025 MN45, 7 and 10 meters across, spinning once every 1.88 minutes, 70 times faster than the physical limit that should have torn a loosely bound rubble pile apart. Getting the observatory built at all required surviving a camera nearly stranded by a trucking strike, a 3mm focus problem solved, through painstaking trial and error and a cooling system failure that risked contaminating the entire instrument. Right now, the observatory is logging alerts by the hundreds of thousands each night, building toward its first full public data release sometime between June and August of 2027. And whether 2025 MN45 was born solid or spun itself into something stronger than expected is still genuinely an open question. If you want to know what Rubin finds next, because with millions of alerts a night now flowing in, something else this strange is only a matter of time, subscribe and turn notifications on, because I will be covering the next anomaly the moment a peer-reviewed paper confirms it. Here's my question for you. Does a discovery like this make you more excited about what's still out there, or more unsettled that our models of something as basic as what asteroids are made of were wrong this whole time? Tell me which one in the comments. I read every single one.